Hi, I'm Paul Keoghan from GK Tuition, and in this video I want to talk to you about inferential statistics. The question I've chosen to go through here is 2016 Paper 2 Question 9. In this question, we're told that the annual income earned by people in full-time employment is normally distributed. So if it's normally distributed, that means I can apply all my knowledge of inferential statistics to the normal distribution. So normally distributed, I can use all the formula on page 34, 35, 36 and 37 in my log tables. It tells me that the mean of this normal distribution is 39,400. So it's just very important here that you know that this is a mu as opposed to an x bar. So x bar is the sample mean. If I had taken if I had surveyed 100 people and asked them what their annual income was and then got the mean of that, that would be a sample mean. If I did a survey and then that allowed me to come up with the mean of the people that I surveyed, that would be a sample mean. However, in this case, it's telling me mu, which is represented by the population mean. It's telling me that if I got the average of every single person in this population, the mean of their salary is 39,400. Or in other words, the mean of the normal distribution itself is 39,400. So make sure you understand why I'm representing that as a mu as opposed to an x bar, which is a sample mean. It tells me the standard deviation of this normal distribution is 12,920. So the first thing that I would do here is I draw just a rough sketch of my normal distribution. So I have a normal distribution and I know the mean of it is 39,400. In part A of this question, we're asked to work out the percentage of people who are earning more than 60,000 euro. So in this normal distribution, 60,000 is going to be roughly around here. And I want to find the percentage of people that are earning more than 60,000 euro. So I'm going to need to use page 36 and page 37 in my log tables to work out the percentage of figures that are greater than 60,000. But if you notice, the problem with that is in order to find those figures, I need to have a z-score. I need to convert my 60,000 euro into a z-score. So in this case, what we need to do is go back to page 34 and use the standardizing formula. The standardizing formula will allow me to convert my 60,000 euro into a z-score. The standardizing formula is given as z is equal to x minus mu over sigma. So I've been given all my information, I can just sub it straight in. So in this case, my z is going to be 60,000 minus 39,400. So basically I'm comparing my sample, I'm comparing the 60,000 to the mean of the sample. And I'm dividing that by the standard deviation. And if we do that, in this case our z-score works out as 1.59. So let's draw another sketch of our normal distribution. In fact, what we're looking for, I'll mark my mean is 0 and my z-score is 1.59. So in fact, what we're looking for in this case is the percentage of figures in any normal distribution that are greater than a z-score of 1.59. So actually, this sketch is a lot more useful than this sketch, because if you notice that this sketch looks a lot like the one at the top of page 36 in my log tables. So what I want to do to find this percentage, I need to find the probability that z is greater than or equal to 1.59. But you should recognize that in your log tables, you can only work out the probability that z is less than a figure. So if you go to 1.59 in your log tables and read the corresponding p-value, you'll actually find the figure they give you is the percentage of figures to the left of 1.59. as opposed to the figures to the right of 1.59. So if I have a greater than sign here, in order to work out this section, it's going to be 1 minus the probability that z is less than or equal to 1.59. In other words, it's 100% of the figures minus the amount of figures that are less than this. So 100% of the figures minus these figures, I'll just be left with the figures that are greater than 1.59. If you read this straight off your log tables, you're going to get 1 minus 0.9441. 1 minus 0.9441 works out as 0.0559. So that tells me the number of figures that are greater than 1.59, or in other words, greater than 60,000. Now I was asked to get my answer as a percentage. So to convert this into a percentage, I'm going to multiply it by 100. Multiplying by 100 essentially just means you're moving the decimal place 2 places. So it actually becomes 5.59%. And it asked me to leave it to 1 decimal place, so clearly I need to round up to 5.6%. So in this case, I've worked out that 5.6% of the figures in any normal distribution are greater than 1.59. And what that means from a practical sense is that in this normal distribution, 5.6% of the population earn more than €60,000. In the second part of this question, we're told that the government offers a subsidy to the people earning in the lowest 10% of the income earners. So I need to figure out what figure constitutes earning this subsidy. Or in other words, what is the Z-score for which 0.1, the proportion of the population earning less than this is 0.1. So once I find my Z-score, I'll be able to find the corresponding X value or the corresponding wage. So I recommend maybe we'll do the video out and then watch it again, just because once we finish the question, it makes a lot of sense. So I know that the proportion of figures less than this are 0.1. Or in other words, 10% of people earn less than this figure. So what I need, I know the proportion, and I need to find the corresponding Z-score. So in order to do this, I'm using my log tables on page 36 and page 37. Except notice that we're using it the opposite way to how we usually use it. I know what the proportion is, and I'm looking for the Z-score. Remember, the proportions are the figures in the middle of the table. The Z-scores are the figures along the side. So actually, we know the figure in the middle, and we're looking for the figure at the side. The smallest proportion in my log tables is 0.5. So it's actually impossible to find this Z-score. And the reason for that is because this one is less than the mean. If this is 0, any figure less than the mean is clearly negative. And there's no negative Z-scores in my log tables. So rather than finding this Z-score, I need to find the corresponding Z-score on the positive side of my normal curve. So in fact, I need to find the Z-score that's out here. I need to find the Z-score for which the proportion of figures greater than it are 0.1. Okay? If the proportion of figures greater than it are 0.1, then that means the proportion that are less than it are 0.9. Or in other words, 90% of figures are less than this Z-score. So I know that my proportion is 0.9, and I'm trying to find the corresponding Z-score. So to do this, we literally just scour through our log tables, page 36 and page 37, find the closest value to 0.9. Now the closest value that you should find is 0.8997. The closest we get to 0.9 is this. And you should notice that if this is my proportion, the corresponding Z-score is 1.28. So basically what I've figured out is that if my Z-score is 1.28, then that means 90% of figures are less than that and 10% of figures are greater than that. And the reason that that is useful to us is because if we remember, this is a perfectly symmetrical graph. So if 10% of figures are greater than plus 1.28, that means that 10% of figures are less than minus 1.28. So I know now the Z-score must be minus 1.28. 10% of figures are less than it, 90% of figures are greater than it. So with that in mind, let's just consider what we know. I know that the mean of the normal distribution is 39,400. I know the standard deviation is 12,920, and I know that Z is minus 1.28. So if you just look back to your standardizing formula, my standardizing formula is given as this. I've got 4 variables in this formula. I clearly know 3 of them, which means I'll be able to find the other one. X, of course, in this case, being the amount of income you earn in order to be in the lowest 10%. So now all we need to do is sub in our values. So my Z in this case is minus 1.28, my X is unknown, my mu is 39,400, and my standard deviation is 12,920. So the easiest thing to do here is to multiply both sides by 12,920. And if we do that, we get 16,537.6. So minus 1.28 by 12,920 is minus 16,537.6, which is equal to x minus 39,400. So clearly if I want to get x on its own, I'm going to add 39,400 to both sides. And if I do that, I end up with x is equal to 22,864. It asks me to leave it to the nearest euro, so if I round that off to the nearest euro, it's 22,864. So that's my final answer in this case. Okay, so it's important that you understand that one. I think a number of times in Leaving Cert higher level maths, I want you to link part A part 1 and A part 2. What we did in A part 1 is the exact opposite of A part 2. In A part 1, they told me the amount people were earning was 60,000. I converted that into a z-score, and then I used my log tables to convert the z-score into a p-value, into a probability, into a proportion. However, in this case, they gave me the proportion, 10% of figures are less than this value. I had to convert that into a z-score, and I had to convert my z-score then into a salary or into an x value. In A part 3 of this question, we're told that 1,000 workers were surveyed, and that the annual income of these 1,000 workers was 38,280. We're asked to test the hypothesis using a 5% level of significance that the mean annual income of full-time workers has changed. So in other words, right, my n is 1,000. I tested 1,000 people, and the sample mean, or the mean of my sample, was 38,280. But it's been claimed that the average of the entire population is 39,400. So I want to figure out, why are these two figures different? Is it just coincidence, or is it because mu is no longer relevant? Is it because that the 39,400 is actually wrong? Okay, so now there's the wording on this question. It's very important in terms of our null hypothesis and our alternative hypothesis. The question says, test the hypothesis that the mean annual income of full-time employment has changed. Test the hypothesis that it has changed. Okay, but that is not my null hypothesis. The null hypothesis is always that there's no change. So even though the question says, test the hypothesis that it has changed, my null hypothesis is that it hasn't changed. Or in other words, that mu is 39,400. So my null hypothesis is the opposite of what they've said in the question. The question says, test the hypothesis that it has changed, but a null hypothesis is always that there's no change. So, in fact, my alternative hypothesis is that the mean is not 39,400. And that's the way they've worded it in the question. So I'm going to assume that it hasn't changed. That's my null hypothesis. And the alternative hypothesis is that it has changed. So just be very careful with the wording there. The other thing I want to highlight in terms of the wording is the 5% level of significance. Now, you know in class, the question says 5% level of significance. I always recommend doing a one sample Z test. So on the top of page 35 in our log tables, we've got the formula for a one sample Z test. Now, I just want you to be aware that usually in the marking scheme here, you actually got the marks if you use the confidence interval. But if it says a 5% level of significance, I want you to get into the habit of using a one sample Z test. That's really important. Now, there's two types of one sample Z tests that are on the course. There's ones for the sample mean and there's ones for the proportion. So we just need to be fully sure of which one we're actually using. So either we'll be using sigma over the square root of n, or we'll be using the square root of p times 1 minus p over n. So we just need to figure out, are we dealing with the standard error of the mean or the standard error of the proportion? Notice both of these are in our log tables on page 34. In this case, it's relatively obvious. We've been given a standard deviation, we've been given a sample mean, so clearly we're going to be using the standard error of the mean. So for this question, the proportion is irrelevant. And if we're using sigma over the square root of n, that means we're using the one sample Z test as it is in page 35 in the log tables, which is x bar minus mu divided by the standard error of the mean, which is sigma over the square root of n. So once you've identified, right, 5% level of significance means I'm using this formula, and just doubly check, right, I'm clearly using sigma over the square root of n because I've been given a standard deviation and there's a sample mean involved. Now I can just plug in all my values and find the z-score. So I know the sample, in this case, the sample mean was 38,280. And I want to compare that to the mean of the population, which is 39,400. And I want to figure out, was it just a coincidence that these figures are different, or is it actually statistically significant? So I'm just subbing in all of my values. And again, we can just plug that straight into our calculator. If you plug this figure into your calculator, my z-score is minus 2.74. So straight away, you should recognize that this is a really, really low z-score, and it's outside of our confidence interval, or it's outside the 5% level of significance. So what I want you to do, maybe pause that. That's the maths. What I find what students really struggle in is how to actually conclude these questions. So in the next frame, I want to talk to you about how you can conclude this question in a really thorough manner. Okay, so as I always tell you in class, when you're concluding these hypothesis tests, I want you to do it threefold. I want you to have three different things that you're going to do in your head. The first thing that you should do is you sketch a normal curve. You mark in 1.96 and you mark in minus 1.96. If my z-score had landed between these two figures, I would have failed to reject HO. However, if it's bigger than 1.96 or less than minus 1.96, these are my rejection zones, and I would actually have to reject HO. So you notice I've marked those in, and then I've also marked in where my z-score was. So my z-score was very negative, so it's way out in my rejection zone. So graphically, that explains my conclusion. Mathematically, to explain your conclusion, you should say that z is less than minus 1.96. So because z is less than minus 1.96, therefore I reject HO. Because z is out here, I'm rejecting it. So mathematically, that explains my conclusion. And then in terms of the actual question, remember the null hypothesis was that the mean annual income has not changed. So I've rejected my null hypothesis. So my conclusion is that the mean annual income of full-time workers has changed. And notice that I've actually just quoted the way they worded it in the question. So I've just rewritten part of the question. The mean annual income of full-time workers has changed. So I've explained it graphically, mathematically, and in English. So I think just be really thorough with your conclusions. Often it's hard to tell when you're in the exam which one is actually needed. And in a lot of cases, you don't actually need all three of them. But I think you won't be sure which ones you actually need to get the full marks. So as I always say in class, just make sure you conclude threefold. I think that's really important. Okay, so in part B of this question, we're told that the Research Institute surveyed 400 farmers. And that the average salary of these farmers was 26,974 with a standard deviation of 5,120. Now it's vitally important that you recognize the population in part B of this question is entirely different to the population in part A of the question. In part A of the question, the population I was referring to was everyone in full-time employment. Whereas the population in part B are farmers, I'm just getting the average salary of the farmers, but not everyone else. So the population in part B is just the farmers from this country, whereas the population in part A was everyone in full-time employment from this country. So with that in mind, the figures to part A are irrelevant to part B. Now you've been asked to come up with a confidence interval, a 95% confidence interval based on these figures. So you should recognize that there's two different types of confidence intervals on the Leave Insert course. You're either going to be using the standard error of the mean, or you're going to be using the standard error of the proportion. So you should be able to figure it out. It should be quite obvious based on the information we've been given. We've been given a standard deviation, a sample mean, and a sample size. So clearly we can't use the standard error of the proportion. Clearly in this case we're dealing with the first one, or the standard error of the mean. Once you've identified that, we know the formula for a confidence interval is x bar plus or minus 1.96 times sigma over the square root of n. So let's just sub in our figures and then we'll consider what this formula actually means. So x bar was the result of my sample which is 26,974, plus or minus 1.96 times the standard deviation divided by the square root of the sample size, which is 400. And if we just put the right hand side here into our calculator, if we just plug this into our calculator, it works out as €501.76. At this point now, I want to talk to you about what each of these figures mean. So x bar is clearly the sample size, the result of my sample. The 1.96 allows me to be 95% accurate. Now the only one on the Leaving Cert course, the confidence intervals they ask you for will always be 95% confidence intervals, which means that it'll always be a 1.96 here. And then this is the standard error of the mean, which is sigma over the square root of n. So it accommodates for the size of the sample and the standard deviation of the sample. Now, in an ideal world, if this research institute wanted to figure out the average salary of farmers in the country, ideally they would survey every single farmer in the country. They'd survey every single one of them and they'd get the exact mean. But obviously, maybe there's 1 million farmers in this country. So it's impractical to survey 1 million people and get their average salary. Realistically, all they could do is, what they've done in this case is they've surveyed 400 farmers. The average of those farmers, their average salary was 26,974. And we can use this figure as a guideline to figure out what would the average of every single farmer in the country be. If we surveyed the million farmers, what would the average salary be? So it's important to recognize, let's pretend that this country is Ireland. Let's say that the Research Institute surveyed 400 farmers from Westmeath, okay? And the average works out as 26,974. That figure that's not necessarily the average of every farmer in the country, because maybe the farmers in Westmeath are a little bit wealthier than average, or maybe they're a little bit poorer than average. So the €501.76 describes the degree to which the result of my sample might be wrong. So based on the fact I surveyed 400 farmers, the result of my sample could be off by, at the very most, €501.76. And I don't know whether this figure is lower than average or it's bigger than average. So in order to accommodate for both scenarios, I need to add on the potential error and I need to subtract the potential error. So in the next line we introduce mu. Mu represents the population mean. So the population in this case being the average salary of farmers in the country. So the average salary of every farmer in the country, there's a 95% chance it lies within this region. And to work out my region, it's the result of my survey minus the degree to which I could be wrong. The result of my survey minus the degree to which I could be wrong, and the result of my survey plus the degree to which I could be wrong. So now all I need to do is add this figure and subtract it. So the maximum value in this case is 27,475.76, whereas the minimum value in this case is 26,472.24. So what this confidence interval represents is if the Research Institute surveyed every single farmer in this population, maybe 1 million farmers, there's a 95% chance that the average salary would lie between this figure and this figure. So the result of my sample actually just acts as a guideline, and then I know the actual mean of the population is somewhere in this region. So my final answer, my 95% confidence interval in this case, is this figure here. In part C of this question, we're told that farm size is not normally distributed, and that the Research Institute took many large random samples of farm size and created a sampling distribution. And we're asked to give a reason why they might do this. Now, the answer is written here, but I want to explain it as well. So the answer here is that the distribution of sample means will be normally distributed so long as the sample size is greater than 30. So that's what you need to write to get the marks. But I want to just explain to you what it means as well. What we're referring to here is the central limit theorem. So if you look in your notes where we have our title and central limit theorem, that's what this question is referring to. So it's referring to the central limit theorem. It's telling me that farm size is not normally distributed. So maybe there's a whole load of small farms and then a whole load of big farms. Or maybe it looks something like that. It's not a normal distribution, which means that if it's not a normal distribution, I can't do a confidence interval, I can't do a hypothesis test, I can't do any inferential statistics on this data. However, obviously the Research Institute want to do a confidence interval, and they want to use inferential statistics to analyze the data. And in order to do that, what they're going to do is they're going to take a load of large random samples of farm size. So let me give you an example here. Let's pretend that this country is Ireland. Let's say we go to Meath and we take a sample, we survey 100 farms in Meath, and the average size of those farms is 100. Okay, let's just call it 100. Then I go to Kildare and I survey another 100 farms, and the average of all of the farms in Kildare works out as 110. And then I go to Carlow, I do the same thing, and the average of those farms works out as 90. I do the same thing again in another county, the average of those farms works out as 115. So on. So I go all around and I take a whole bunch of large random samples of farm size. So even though if I plotted every individual farm, there'd be loads of small ones and loads of big ones. It's not a normal distribution. But if I plotted the average farm size in each county, or in other words, if I get a whole load of sample means and I get the average in each county, and if I plot them, they will form a normal distribution. Even though the size of each individual farm is not a normal distribution, the average size of a farm per county or per sample will be a normal distribution. And then I'll be able to carry out confidence intervals, hypothesis tests, or any kind of inferential statistics that I want. So that's why my answer makes sense. So the reason that the Research Institute are going to take a whole bunch of random samples and create a normal distribution, it is because they're going to form this shape. In other words, the distribution of sample means will be normally distributed. The key here is, I've said, as long as n is greater than 30. In order for this to be accurate, you have to take at least 30 samples. I'd have to go to at least 30 counties and get the average farm size in each one. So your answer there, all you need for your answer there is this. This second bit here was just my explanation. So just be aware that what they're referring to there is the central limit theorem. In the final part of this question, we're told that the Research Institute also carried out surveys on agricultural land. We're told that the margin of error is 4.5%, and we're asked to find the sample size. Now, you should be aware that there's 3 different margins of error on the Leave Insert Higher Level course. One of them is that E, which is my margin of error, is equal to 1.96 times sigma over the square root of n. I use this if I'm dealing with the standard error of the mean. This is a margin of error allows me to be 95% accurate. Clearly in this case there's no standard deviation. I'm not dealing with the standard error of the mean, so I'm not dealing with that one. The second most common one then, is that the margin of error is equal to 1.96 times the square root of p times 1 minus p over n. I use this margin of error if I'm dealing with the standard error of the proportion. However, clearly in this case it's nothing to do with the standard error of the proportion. So that leaves us with the third one and the most straightforward one. The only margin of error that's on the Leave Insert Ordinary Level course is the margin of error is equal to 1 over the square root of n. And this one is also 95% accurate. And it's rarely applicable to the Leave Insert Higher Level course. In a question like this is really the only scenario where it can come up. If they just gave you n and asked you for the margin of error, or if they just give you the margin of error and ask you for n, then you have to use this one. So it's very rare that you actually have to use this one, so it's vitally important you don't forget about it, because it is on the Leaving Cert higher level course. So in this case, they've told me the margin of error is 4.5%. Well, percentages are no good to me, and I need this as a decimal. So if I divide 4.5 by 100, to get rid of my percentage, it becomes 0.045. So my E that I'm going to sub in is 0.045. So I know that 0.045 is equal to 1 over the square root of n. And now I've got one equation, one unknown, so it's going to be relatively straightforward to find the value of my n, which is my sample size. So in this case, probably the nicest thing to do here first is to try and get rid of my square root. In order to get rid of the square root, I need to square both sides. So if I square the left-hand side, I'm going to get 0.002025. If I square the right-hand side, well, the top 1 by 1 is just 1. The square root of n by the square root of n is n. The next line, I suppose I can multiply both sides by n, and I'll be left with 0.00205 times n is equal to 1. So obviously, if I want to get n on its own, I'm going to divide both sides by 0.002025. And if I plug that into my calculator, it works out as 493.82. Now, clearly they didn't interview 493.82 farmers. Clearly this answer has to be a whole number. But unfortunately, there's a bit of ambiguity in the question, and it's not entirely clear whether you should round up or round down. So in the marking scheme that year, they actually accepted 493 or 494. Because there's a little bit of ambiguity there, so they actually accepted either one. So you can say that 493, or you can say 494. It doesn't actually matter which one you said, but you just round up to a whole number. So again, I think this whole question 9, this is really good, especially the last two parts. I think like the central limit theorem and this margin of error, there's just a lot of theory from your inferential statistics, a lot of the tiny little details. In order to do well in that question in 2016, you would have had to really know your theory. So I hope everything in this video made sense. If not, then just let me know in class and I'll try and explain it differently. And as always, if you want, send me an email and I'll clarify whatever you're unsure about.